This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
Okay, I had a prepared presentation, but this is not prepared. First of all, I wish to thank Charlie for inviting me here, and the best tribute to his career is the variety at the level of the people attending this event. As Charlie indicated, we don't want to teach you anything, but we would like to hear your reactions to what we say and speak about things that are current and controversial if we can. Now, let me say, I can say a few things that I probably am the oldest person to have known Charlie from the time when he was a graduate student at MIT. His advisors were Ed Friedman and John Green, wonderful people. And I began very early to have great respect for Charlie for his open-minded interest in various fields and so on. Then I moved out of Princeton, went to Stanford and UCSD, where I'd been in the faculty as an assistant professor. But then we had an academic year, which later I will call a summit, at Trieste, where the best people in plasma physics gathered together. There were seminal contributions coming out of there. And we have four friends here, Charlie, Roel Sagdev, and Herb Burke, who are present. We are all still alive and grateful that we are here to celebrate. It's almost 50 years. It's 49 years since we met in Trieste. So in those days, I was doing space physics on the side. And the head of the American group, we had three groups: a Russian group headed by Rold, an American group headed by Marshall Rosenbluth, and everything else was headed by me, but we are only two Frenchmen. Marshall Rosenbluth was the senior person, did not like me to work on space physics, but Charlie supported me. And I could tell you a number of episodes about that, how we wrote the first paper, kind of in a clandestine way, on the Earth's magnetotail and the origin of the auroral substone, which is still valid. So now the title of this section, oh, by the way, I forgot to tell you about myself. I went back to Princeton after Trieste to the Institute for Advanced Studies. And then since at Princeton there was not much interest in space physics, we were entering into space. I got a visit by Bruno Rossi. They were doing X-ray astronomy at MIT. And I was very intrigued by that. It was a new kind of plasma physics, so I moved there. Then I had the idea while I was there that one could use a fusion experiment to simulate the first X-ray stars that were known at that time. That was 68, 69. And we knew about 7 about that, not many. And 2 of them had very different spectra. One was Scorpio X1 that was very thermal, and the other one, the Crab, that was very non-thermal. Now the sky is full of X-ray stars and gamma-ray stars. So then I felt that I could use what I've learned from my Russian friends about Tokamak experiment to make something that will go beyond the Russian Tokamak to simulate the X-ray stars, both the Crab that was non-thermal and the Scorpio that was thermal. In trying to simulate Scorpio, we had to go to very high densities. And then in those density regimes, we discovered that the plasma was extremely well confined. So after that, the idea came up that we could use this experiment to prove that the plasma could ignite. So I'm saying all of that story personal because the connection between astrophysics, space physics, and fusion research is very intimate. And it is just correct that Charlie would have included it here. Now, fusion research is very interesting because of that. It has connection to many types of technologies and to astrophysics and space. Since Marty Rees is around, let me say that we learned in the laboratory of a phenomenon that we call the spontaneous rotation. All axisymmetric plasma rotate without injecting angular momentum. And that, I think, is very interesting if you want to explain how angular momentum is transported in cases where you have energy emission. You know, if you have a black hole and you have accretion, you need to export the angular momentum. So fusion research is continuing to contribute to astrophysics. We need to have more conversation, more connection. And this is a good opportunity to do that. Then it would be very interesting to hear from the audience what you think of, what you would like to know about fusion. Because since the time of Trieste, something, oh, there it's in the title, something went very wrong. Something we did not expect. Of course, the Vietnam War has its role, and so there has been a kind of anti-science attitude. And then there was, in the funding of physics, a prevalence of the bureaucracy. For example, we used to have the Atomic Energy Commission, the AEC. When I proposed the Alcator, I proposed it to simulate astrophysics. And the chairman of the Atomic Energy Commission, he said, well, Bruno, it sounds a bit far-fetched, but let's do it. Now, the AEC was destroyed, was substituted in the US by ERDA, and then the Department of Energy, and it never regained the scientific standards, a way of managing things as it had under the AEC. Maybe Charlie can tell you a different story about NASA. And there has been another problem that hampered fusion research. That is the role of the European bureaucracy. Europe is extremely well paid, especially in Brussels bureaucracies. They care about their salaries and so on. So, for example, if you need to do experiment in fusion research, which are experiments, basic physics, they don't like them. They like to protect their, you know, this experiment may prove that in the end there is no hope, or maybe they solve the problem. That will be the end of their careers in terms of bureaucratic careers. So then the Brussels bureaucrat invented a series of so-called experiments that never end. And I will speak about one which is called ITER. Roald is one of the original proponents. There was, you can tell the story better than I, Roald. There was a meeting, some meeting with Bush and the chairman of the Soviet Union. And both Roald and Yevgeny Velikov, part of our community, proposed that we do an experiment, you know, that would get the US and Russia to collaborate together. But let me say, about 8 days later, Roald called me up saying that he was not happy about this proposal in any way. That proposal then ended up in the hands of the European bureaucrat. It became so big that it was subject to an examination by the White House, which I was part, that was under Clinton. We decided, together with the present science advisor to Obama, to get out. That was ITER. But then under George W. Bush, we, in order to appease Blair to his initiative to enter into the Iraq war, the US entered back into ITER. Now, it's an enterprise that will cost between 55, it has been estimated officially, and $72 billion without commissioning. So that means that if you follow fusion along those lines, fusion research in terms of producing a demonstration that you can burn a thermonuclear plasma under controlled conditions will never be done in practice. And how could we go from the excellence of Trieste to this point? It would be something that would deserve a deeper analysis. In any way, that is the story. So, yes, now I forgot to tell you that, you know, that for many of you who may not know, fusion research is centered on the idea to reproduce on Earth in a controlled way what goes on in the hydrogen bomb, for example. And if we look back, when we were in Trieste almost 50 years ago, of course, none of us were, all of us were serious people, promised that we would make a power station. But certainly we would have said we would have done the key experiments, and we have not done them. so this is the situation where we found ourselves. Let's see if Herb Burke is a professor at the University of Texas. He was also at Princeton. He was also at Trieste. What he has to say in his presentation. So we interrupt now to ask questions to the audience? Or
if someone has a question.
You have a question?
Interruptions are encouraged.
Yeah, we would like to hear from, yes.
Maybe one question. Why do you think the ITER enterprise, I put it this way, will never really lead to good science and advancements on the future?
Well, that would be too extreme. Let me rectify that. You can always do both sides.
Right, let's go forward.
But with 72,
Let's see, which is the change?
you can do many interesting experiments.
Okay. Oh, I see.
We never demonstrated you can make fusion because it cannot ignite by definition. And also the goal stated, which they withdrew after we made that panel on the Clinton. I remember that panel. It is not threatened, but it cannot ignite. It cannot even obtain the humble goals that are specified officially. But I'm very sure that something good will come out at great expense, a great deal of time, but will not prove whether you can ignite or not. It's abandoned, that goal. And you had another question? No.
I don't know if you're just comment. I don't know quite what you mean by ignite. There's two ways of, I mean, in principle, Tokamak could be totally self-heating. All you have to do is throw in material. But there's other ways if the confinement is not good enough, and this is the goal of ITER, is to show power amplification.
It is not power amplification. I'm not an engineer, if you don't mind. I can prove to that.
Let's listen. we have somewhat different views, but basically it means that you may not get ignition, but the goal is to get this power amplification. I'll speak with Bruno and find out what he means that it's that power amplification. It's power because you're constantly putting in a certain amount of power, and the hope and the goal, stated goal, is to get 5 times more fusion energy. And actually, if it meets that, this probably doesn't have to go much further and actually get ignition. But I think I think this is a reasonable. It's a reasonable goal. It's likely to do this. The issue about whether it's going to be a fusion reactor, in some sense, ITER will only show the possibility of it, and then there has to be more different types of experiments, even more expensive, unfortunately. But I think, and I think what Bruno is saying, that some good will come of it out of ITER, and the point is it is a good experiment, and it's going to produce something good, and how much fusion energy is really the critical aspect of what it has to produce. But this is not my talk, but this is my comment.
Bruno, it would be interesting if you would clarify how much it was promised to be given for ITER at the inception of ITER project. How much money were promised? So people would see the,
Yes, yes. I'm glad you are saying that. The initial cost was about $5 billion promised to the US. Then, after we had gotten out of under Clinton, then it began to become 5 billion euros. Then, of course, we know it was not true. He's a great theorist, but he's not an engineer, my friend. So I sent for him. We are friends. So Then, of course, we know it was not true, and in private we knew it was at least factor of pi bigger. So then there were hearings in the Italian Senate. At the end of that, the French were compelled to say it would be 16 billion euro.
16.
16.
16, yeah.
16. And that continued.
1-6.
16.
Yeah, 16. And then, of course, which is 5 times the 5 that they used to say. Then we know that that was not true either, because the machine had never been designed. Still, the design is very incomplete. Okay? Then, for some reason, it had nothing to do with that. The news of those costs went to the US Senate, so they ordered 2 assessments of the cost. Now, as I said, there is one that is 55 billion without commissioning, and the other one is 72.2. And 3 weeks ago, the Senate recommended officially that both the State Department and the DOE would get out of ITER. Why the State Department? Because informally, the DOE decided they would not pay for the experiment, since it was a diplomatic type of initiative. They asked the State Department to pay for it. But now, with this recommendation of the Senate, I don't know what will come out.
Okay, can we, let's go back. I mean, we could pan this for a long time. Let's go back, and I'll talk about the basics, and then we can come back.
Get everybody else on the same page, and then we'll go back again.
Yeah. Okay. Well, this is self-generating discussion. I push away the moderator. Anyway, let's go back. Let's go back more than 50 years, because that's more than 1962, as I think I met Charlie. We were fellow graduate students together. I met Bruno at the same time, and I met Marsha Rosenbluth a year or 2 later, who has been critical to our careers over the years. And I could say that ITER, just to get it back, is in part Rosenbluth's brainchild. He spent several years here on a scientific committee assessing ITER, assessing the physics of ITER, and actually producing some really interesting physics issues, like the problem of runaway electrons. It came from the La Jolla community, because that's where the working group was, and then it died when the U.S. got out of ITER in the 90s. But anyway, the aspect of ITER as being the next step, Marshall Rosenbluth was a great proponent, and I wish he was here to meet the criticism that I hear today. What? Yes, I mean, I'm sure he wasn't on agreement about shutting that on either. I'm glad to hear that. Anyway, let's go back to basics. There are 3 different ways to confine plasmas for fusion. One is gravity, and this is the one I say Charlie has been in part looking at the fusion products, but and the gravity produces fusion in the stars, as you well know. And there's one important star, and that important star is the sun. And one aspect of, if you look carefully at this picture of the sun, is you have these flares coming out. These are the magnetic fields. They don't do much to confine hot plasma in the sun, but ultimately this is the way we're trying to use on Earth. So what's happening is in the 50s they figured out how to get fusion on Earth, and this is the hydrogen bomb. And actually, it's quite interesting that it only took a couple of years to actually get the needed plasma confinement to produce the hydrogen bomb, and that's done because you're able to compress matter to many times the natural density, and with higher densities, you get your requirements for confinement gets shorter and shorter. That is, a shorter and shorter time for confinement. But so you could try and do the same thing on a small scale. You take a small pellet, you take extreme pressures that are produced by either laser light or accelerators, and you compress the pellet, and the hope is to get fusion. There's a big experiment in this in Livermore. They were too optimistic. They expected last year or two, they expect they would get the ignition conditions, and unfortunately, they have to backtrack and figure out how to get it to work. But this is one way. It's still a possibility that it will produce fusion, but there's the alternate way that I've been mostly involved in, and that's magnetic fusion. And in magnetic fusion, what you have is a magnetic field, and you look at the single particle trajectories in a magnetic field, and they spiral about the field. The straight line is the field, and we get the spiraling. So we have two-dimensional confinement, and it's very simple, but unfortunately, we haven't got anything long enough to have two-dimensional confinement work. So what you want to do is take this field and close it around itself. It's like a snake biting its tail, and then what you get is a toroidal machine. That is, the plasma is contained in this donut that you see, and inside is plasma. And this is a picture of the first tokamak ever built in Russia. It's called T1, and it was conceived by Tom and Sakharov, the very famous Sakharov, very famous Tom, but this is who we know, and in order to get the snake to bite its tail, is you put a current in the direction of magnetic field, and then you get something that actually confines in 3 dimensions. There was the Tokamak continued, and the third Tokamak, T3, reported that you have hot plasma that is in the several kilovolts in energy. And it was interesting that the entire Earth community did not believe it, because in toroidal experiments that they had done, where they have an electric field going around the torus, all you got was runaway electrons, and what you wanted was you didn't want an accelerator, you wanted to produce a thermal plasma in the kilovolts temperature regime. This wasn't believed. So what happened is in order to get it to believe, is the Russians knew how to make plasma confinement. They didn't know how to make lasers. To get lasers, we had the first Cold War experimental collaboration. It was with the English, some famous physicists came there, scattered laser light, and the Doppler shift from the laser light informed them that the system was still hot. So what then arose is what I call tokamania. People had all kinds of experiments around the world. Most of them were shut down and converted into tokamaks, and the world loved tokamaks. Now, tokamaks did a very good job in confinement, but still there was an issue. And the issue was that if you put in power, you couldn't confine much better, and they were having problems. And then there was a breakthrough in 1982, which occurred at the Aztecs facility in Germany, near Munich. It's Garching, Germany, where it was, at the Max Planck Institute. And here's what happened. Usually plasmas are ohmically heated. That is, the resistivity gives you I square R heating. And then you put in an auxiliary heating source, which are neutral beams, at this case probably about 20, 30 keV, and you inject it into the plasma, and this is the heating. So what they see is the plasma pressure suddenly increasing, but then it can't go anymore. You put in more heat, you still, that is, you increase the beams, and you can't get much beyond this point. And then suddenly they had a discharge where, in one case, one shot, they got this usual thing and no limitation. And then they did a second shot under different conditions, and they got a transition, a bifurcation, if you will. And instead of this little hump saturating, they actually were able to double the pressure. And this is the H mode. And the H mode is what people are building on to get to fusion. So the L mode, a modern increase of plasma parameters, is insensitive to external power increase. You go to the H mode, you have a sudden rise of the stored plasma parameters, though it's still, but once it reaches this level, it now becomes insensitive to increased power. And the other thing with the H mode is that there was really a big change in plasma characteristics at the edge. And what is happening there? So to understand what's happening in the H mode, you could look at what is the pressure, temperature, or density. They're all more or less somewhat the same. And what you see is a sort of a sudden, this is the radius of the plasma. You see a slope in the profile, and then it goes to the edge. In the H mode, you see you have almost double the pressure, but you still see the same slope, and then a very sharp decrease in the pressure. And it turns out this was the transition that was occurring. The bifurcation was the development of the different type of edge conditions, where there was a lot of flow in the plasma at the edge, this flow is attributed to being able to make this flow is attributed to be able to make this large pressure gradient due to the flow shear that could sustain the plasma, but the slope on the inside has to be the same in all cases. And this is a very strange thing, as if it's the profile. The edge conditions this is the knob that is really the heart of the confinement. You have to get this pedestal, as it's called, you have to get it to increase. So what you have then is this base pedestal, and then above it is something that is just a characteristic drop. And so here's the edge that really is crucial to the confinement. And what happens is the plasma on the inside just dribbles out and comes to the edge. And the fact that this could be attributed to is that you reach a marginal stability point that the plasma hovers under, and if you push it too hard, you can only push it these turbulent terrors, they just push higher and push out the plasma to almost maintain this profile. I remember Harold Firth giving a talk about these little demons, or he called them Vietnamese guerrillas at the time, because he gave this talk just when we were involved in the Viet War, and he says the harder you push them, the more these guerrillas push out. But someone even before Harold Firth thought about something like this, and Charles Kendall talked about the electron drizzle in the magnetosphere, and he reported it to me in our great year in Trieste. But there really is this little connection, the fact that you just get, you can push harder and harder, and you get almost the same profile. Charlie noted that years ago. So now there could be an alternative scenario, which was much better if you could get it, and that is you find that you could get an internal barrier away from the edge, and this is much better because if edge conditions change a little bit, this is far less sensitive to the edge conditions, and you get in a place actually, it's due to the profile of the magnetic shear, and often in an internal barrier, the region inside is quite stable, and they've achieved really good conditions. So if this mode could be achieved in ITER, there's technical reasons why it's difficult, but this would be a much better way to have a burning plasma because you're less sensitive to details. So then we want to understand plasmas, and there's big numerical efforts to use the power of computers to reproduce the effect of plasmas. One important group is General Atomics, not far from here, up the hill, and they have a code called gyro, and you see how they simulate almost the entire machine, but there's a hole in the center, and they don't get the edge. So what they simulate is they don't simulate the edge profile, but they simulate the inside. And you see here is sort of an example of the coincidence they could get between experimental fluctuations and the fluctuations predicted in their experiment. You might note these are magnetic fields twisting around in the torus. Here is a picture of the turbulence. The turbulence drives particles across the field and makes the confinement generally worse. And here's a blow-up of what can be seen in this case, the fluctuation level, and this fluctuation level can be compared to experiment. Anyway, the really hard part about trying to do this is not a fluid, is that the fluid, the mean free path has to be, of the particles, has to be much less than the scale lengths of the system. Here, the mean free paths can be thousands of transits around the machine. And the result is you cannot use fluid theory. You have to use, use a theory that can basically has to work in 5 dimensions. And this is, for those experts around, this is actually a Vlasov code, and it has basically a 5-dimensional characteristic to get the turbulence.
Let me interrupt a second. Roland was reminding me, all these codes lead to a diffusion coefficient that we found in Trieste called gyro bond. We wrote a paper.
Okay, so actually you could ask what can these codes do, and one of them is replicate theory that has been that was studied earlier. The other issue is how well you could do predictions, and this, and I could say that you see this limitation is what people are working on now is a way to simulate the edge. And hopefully, when you, again, you have the problem that it can't be a fluid code, it's long mean-free path. And you also have the problem that you have transitions to short mean-free path. So it's really, I would say, an intellectual exercise to get a code good enough to replicate experimental conditions. So that, I would say, is sort of the long-term need for fusion. I must be really way over time. Here is a picture of the fact that old experiments actually produced a copious amount of fusion events. Basically, this experiment was the US effort. TFTR is the acronym for the machine that was used at Princeton University. For roughly half a second, they produced 20% of the fusion power compared to the power they were putting in. And JET produced maybe 80% of the fusion power compared to the power they put in. And this is roughly for a second. But actually, it turns out that the experiment that they're proudest of at JET is one that lasted 5 seconds, more or less the length of time that any shot could last in JET. That may go up to 10 seconds, but anyway, they did it for 5 seconds. They deliberately changed plasma conditions along this way, and they deliberately moved along the lines that were close to the regions where confinement would break down. All along, they had confined the plasma, and in the process, I think, well, you see, it's about a 20% production of fusion for the power they put in, but they had it under great control, and this is their most important experiment. And then you have ITER being built. This gives you the scales of ITER. And not only is the magnetic field in ITER is about twice that of JET, so what you have is a scaling where the ratio of the orbit size, which is called rho, compared to the radius, changes almost by a factor of 10 as you go from this JET experiment that could produce fusion to the next one, ITER, that wants to produce a substantial gain in fusion. So, and this is what we will have as TFTR, not TFTR, ITER, and you might recall the people around T3, the people were bigger than the machine. Here's the people here, here's the person, and this is the machine. It is really, it's going to be a big facility, and the ground is broken now. I have, and construction has started of the building, and I guess around 2000, I expect this machine to be almost ready to operate, and probably takes a...
I think you meant 2020.
No.
2020, yes. And then let me finish.
The truth is to come out. It's not a joke. The official date is that if the machine can be designed, it's not designed yet. It will have the first DT operation in 2034. That is official.
That's official?
Yes.
Okay, good. Okay, oh, sorry. So here's the summary. Creating a quiescent star on Earth has proved to be difficult, but steady progress has been made, particularly in the Tokamak concept, where achieving a plasma burn is feasible. I think right now, if you ask, why don't you do it somewhere else, no other device has the confinement properties of a Tokamak. And the basic point basic big point about ITER is in most plasmas, all plasmas, you have to supply the energy. This will be the first experiment where the plasma ultimately supplies the energy. And plasma has to heat the background plasma. So this is the big thing that has to be done, which cannot be done at the moment with any other device, with perhaps the exception of Bruno's idea, which I'm sure we'll be talking about. So as a member of the field, I think we'll certainly show that controlled fusion power can exist on Earth. And maybe it's, I'd say 2035 will show this. And I hope I'll live to 100 years old, because then I will have seen it. Just about 100. I'll be 98 when that happens. And how long would you have it? Well, the plan right now is for 10 minutes in ITER. That's the first phase when they get controlled fusion. When they improve the machine, they'll tend to go longer. But there's alternate approaches to magnetic fusion, and I think I'm almost finished. And it's, of course, still needs to be pursued. And here is Bruno's idea, and magnetic field is a big thing, because you double or maybe somewhat more than double the magnetic field, you can get to 5 times higher density than you can in ITER, and that means your conditions for confinement is 5 or 25 times. And anyway, it's much shorter. Now, there's other ideas like non-symmetric fields, like a stellarator. This concept was abandoned by Princeton, but the point about a stellarator is you don't get any sudden change, which is called a disruption, that you see in tokamaks, and this is one of the main reasons stellarator research still continues in this world. And it's hoped that one can get a steady state, a truly steady state machine. It's still a torus, and that's the stellarator. And then people really want to go small. For a long time, there was a lot of interest and a lot of support of small things, but DOE in his wisdom cut off all support of these small effects. So small compact tokamak effects. But there's one person, Norman Rostocker, who's also a good friend of all of us, had the idea of trying to use a concept which was called, and built a facility called Tri-Alpha, and he's decided DOE is not a good partner, so he put it on the stock market, and they have support from private industry. And Raul just told me they have support from quite a few Russian capitalists. Okay, and that's almost it. There's much to do, to learn, much to do, and happy birthday, Charlie. Congratulations on a brilliant career, and I'm finished.
Now, if you don't mind, before I have my own prepared presentation, but let me bring up something that came out of fusion. Plasmas, those used are very simple systems, not simple than the atmosphere or anything. You know, they're made electrons, nuclei. But in spite of that, there are collective modes. Modern physics is not acquainted enough with collective mode. And we fail to predict this collective mode. Basically. So that comment will come up tomorrow, and it came to the attention of the administration. So if plasma physicists are not so good at predicting collective mode in a system which is as simple as the plasma, how can you predict what goes on in the climate, the atmosphere? We'll discuss it tomorrow. But it's a serious issue. Now, this might interest Martin Greens. Something that came out from our experiment is that plasmas are self-organized. In other words, you can study collective modes. Roland found some of them individually that come out. But when you have to see how temperatures are distributed, or the density, they tend to distribute themselves over profiles constant, no matter what experiment. In other words, collective modes that take place in different regions, they cooperate with each other. So that should be of interest to Martin Greens, because again, the process of accretion around, let's say, black holes and so on, that self-organization should take place to get reasonable profiles for the velocities. And let me give you an example of something that we failed to predict. If you take this toroidal machine, they're actually symmetric. No matter how you make them, small or big, the low voltage need to introduce the current is always the same. And nobody, including myself, ever explained that. In fact, when we did the jet machine, we predicted to that 400 electron volt, it went up to 2 kilovolts. Again, just to tell you that this word confusion as fundamental aspect that has not been resolved yet. And self-organization is one of those. Yes? Lou?
I'd like to come back to the, not the physics so much as just the politics of fusion and how it grew up. And I'm going to be controversial, I guess. In 1961, I spent the summer as a graduate student in Los Alamos working at Project Sherwood.
Yes.
And at that time, controlled fusion was 20 years away.
They were wrong.
Well, and they've been wrong every 20 years. And the fact of the matter is that human beings and the United States and Russia had gotten accustomed to the fact that within a few years of predicting a big project, things happen. Built the atomic bomb, built a hydrogen bomb, we launched Sputnik, we landed people on the moon, we built major telescopes in space, we started looking at the Earth, looking down. We said we were going to build a big telescope, and we built it. We discovered the Van Allen radiation belts, we said we were going to continue studying them, and we did it. And so if I were a bureaucrat, a scientific bureaucrat in Washington and Moscow and Tokyo and wherever else, and Brussels, is filled with people with very good scientific training. And they're sitting there and they're trying to decide how to allocate taxpayer dollars. And they were told in 1961 that in 20 years we're going to have controlled fusion. That was just 3 years after the big Geneva conference. 3 years, I guess that was 58, was it? And 20 years goes by and we're still in the same place and we're still building bigger machines. So, you know, I think one has to be a little humble here as a scientist.
No, I completely agree with you. I anticipated you. I had a series.
You were before me, of course.
In the same, my presentation I will go, this question came up on the New York Times, great last spring. And then John Boulder explained why it is still working. But let me say,
you may have to, you have a microphone, you better speak at the
those of
microphone.
us that worked on fusion research, we never promised, ask Rold, that we will make a power station in 20 years or so. Actually,
I can go back and look at the book, Project Sherwood, and it says that.
yeah, but were they scientists? I don't know.
Bishop was. I want to be provocative.
No, Lou, you're right.
I was the AEC administrator in 1975 when the toroidal fusion test reactor was named. In the world of electricity generation, test reactor means the one before you go online. And the scientists came up and said, we want to build the Tokamak, we want to build it at Princeton, and so we'd like to build it. And this guy said, well, I'm in charge of the politics, you're in charge of the science, and I'm going to call it a toroidal fusion test reactor so I can sell it. And at that point, he had then, in the minds of all the hard-eyed executives of the electricity company, he had committed the country to building a test reactor. We didn't know how to do this.
It was not.
To start with. And so a lot of it was hijacking of the terminology by the bureaucrats themselves, who were connected to our community and with whom we had bonds, so we couldn't actually kick them out of it.
Yes, yes. Yeah, but I don't have time for my presentation.
Okay, then it's not.
Yeah, this is what, Charlie, that was my presentation. But I agree with you. We were taken over by the bureaucrats. And the case of the fusion test reactor, you are correct. Not only, but they invented something that even deceived our friend. They invented a Q. If you take any person, a yield parameter, the Q factor, if you have a power station, means much power you put in and what you come out. Well, the Princeton Q is what he was referring to. It's not that. So the bureaucrat changed the situation. And this is what, as scientists, we have to admit. We did not defend ourselves.
Well, I don't think it's, I didn't, that's not, my trust was, I think the scientists have some fault is a tough word, but have some fault as well. Culpability. Thank you, Mark.
Robert, it's some.
Think so.
What?
I want to make, is this working? I want to make sort of an aside comment closer to Scripps maybe. You know about the Italian scientists who are being charged, who have been found guilty and could serve a prison term if they. Anyway, they're still fighting it. But the point was is that there was burbling in some place in Italy, and they had a scientific conference, and the scientists really didn't say very much. Could be predicted, but the bureaucrats said that scientists said that the scientists declared that all the burbling, the seismic burbling, will go away, and you can return to your homes. And the next day, there was an earthquake, and now the scientists are now have been declared guilty of malfeasance or whatever it is. So that is an interesting thing. So there's about 2,000 people in the fusion community, and maybe we should all go to jail.
Okay, I wonder if I could you project I will show a few parts of my presentation. We have a few minutes left.
Yeah, just a few.
Yes.
And then I'd like to make a summary comment.
Yeah. Can you project let's see, where is my? By the way, the so-called scientists in Italy, they were correctly convicted because they assured that they could predict things. And the scientific community has condemned them as well. I am Italian, I go there, I can assure you. Okay. Okay. Now, we already spoke about the anti-science attitude, the bureaucrats and so on. But unfortunately, the subject that we will speak about tomorrow, the problem of energy on the global scale, the problem of energy on the global scale has become quite severe. So if we had provided fusion, it would have been something good. And I think, in spite of all the flaws, the invasion of the bureaucrat, I think we should still pursue that. But of course, without making false promises. I may remind Lou that once I testified in Congress or in the Senate, and they said, but Professor, if you are so ignorant, why do you want all that money? In other words, by confessing what you don't know, no? It's not very successful. So let me see if I can go through very fast. All right, so this argument that Lou Lazzarotti brought came up. There was an article on the New York Times that was read in the New Yorker. Let me go quickly. This is the ITER. As you can see, it is not just the plasma. There have been problems in management and so on, but the press did not get the idea that there is still not a design of the machine. So there are all sorts of difficulties. This is the construction. All right. Now, John Holdren is a friend, but also is the science advisor to Obama for the second term.
He started life as a plasma physicist.
Yes, you remember that, Charlie. And he was the chairman of the committee that under Clinton we decided to get out of ITER. And then he said that in spite of all the difficulties that we see, that we should pursue fusion research. So let me continue on that. And that is something that, there is something in Italian, but at the same time, when we were in that committee under Clinton, he pointed out that really the goal of ignition is very important. Ignition occurs when a deuterium tritium plasma, which is the simplest to ignite, you heat it, and then you turn off the heating, and the fusion products deposit their energy in the plasma, and they stay heated by itself. producing an ignited plasma will be a truly notable achievement for mankind and will capture the public's imagination. Resembling a burning star, the ignited plasma will demonstrate a capability with immense potential to improve human well-being. Ignition is analogous to the first airplane flight or the first vacuum tube computer. As in those cases, the initial model need not resemble the one that is later commercialized. Much of what would be learned in the Tokamak ignition experiment would be applicable both to more advanced Tokamak approaches and to other confinement concepts. So this is why at MIT and elsewhere, we had a similar program in Italy, and now we have collaboration since several years now with the Russians on that. We have collaboration with the Japanese. We concentrated on producing an experiment which can demonstrate ignition, the real one. And so why pursue, again, this research on nuclear fusion? These things we have already said. You see that we can provide knowledge which is important to astrophysics and other fields. There are being unexpected discoveries. I already mentioned the self-organization process that's still for which we don't have theories. The same is true also in other fields. But probably our papers were the first one. They were written in 1980 on self-organization. Okay, this is what our dear friend Marshall Roosevelt, not only with us, said about burning, fusion burning. And of course, when you refer to experiment, he said that the Fermi paradigm, that a good scientific experiment is one with a 50% chance of success, may apply here, although for such a major venture, the bar should not doubt be somewhat higher, at least for meaningful partial success. And that refers to the Ignitor experiment. And again, there is a phrase by another dear friend. He was at Princeton where Charlie and I were there, that we should have a flame before worrying about the boiler. That is, before promising a power station, we should have a flame.
That's not inconsistent with what I was saying.
No, I never disputed you, except that you have to acknowledge that we were ineffective against the bureaucrat, if you want. But these are, the scientists speak that way. They never promise power stations. All right. Now, I think I told you that the US re-entered ITER under Bush. He wanted to get the support of Blair to invade Iraq, to make war in Iraq, and Blair had an advisor, he's a chemist, I don't pronounce his name, but I remember it. He said that if you make ITER, you would put electricity in the grid in 30 years. That we know is not true. So Bush went back, and some of us, including me, objected, but there was a document, the DOE, where they said that they would go along, but they also said they would go along in collaborating with the ignition experiment that we had started in Italy, and now we want to carry out together with the Russians. So there is Roald and Velikov who proposed the ITER, but then Roald disassociated himself very early, and he's part of a US group that support the Ignitor approach. Ignitor is like what you used to call in plasma physics, the Q machines at Princeton, quiescent plasma machine. It's an academic experiment. Okay, this again to show you what the problems of ITER are. This is what I call the ITER precipice. If ITER, even with the reduced goal, has a current, it is supposed to create a current of 15 megaamps under conditions which are not quite stable. If that is not true, a little bit, there is a precipice. So the probability that we achieve its goal, in my opinion, are very low. And again, I will not go further. This is instead the academic experiment that came out of the experiment that made the simulation to Scorpio X1. This is the Ignitor. It's based on the high field approach, so it's much smaller. And the Russian has started to make a machine like that, but they did not do the design properly, but they built all these structures. So they spent $1.2 billion in Troitsk, next to Moscow. So Velikov came to see me one day and said, Bruno, but we built everything. So if you build a car, for example, in Italy, and we have the rest of the equipment ready to do it. So basically, the construction of the car will cost about $77 million, 77 million, much less than ITER. And as you can see, the dimension of the machines are quite small. 132 meters is the major radius. The minor radius is half a meter, and the volume is 10 cubic meter. By comparison, ITER is 800 cubic meter. So there is a huge factor. And for those of you that are knowledgeable in plasma physics, why is it made like that? It's not only in order to do something small and cheap, but there is a field that is produced by the economy, which is called colloidal field, which is 3.5 Tesla, which is a record, because the reactivity goes like the fourth power of that. So this plasma will be 100 times more reactive than ITER, if ITER can be built. I don't think I will go further. This is a comparison. And this is what I pointed out, that the power of the heating of the fusion products. You know, deuterium tritium gives a helium nucleus and neutrons. The helium nuclei, the alpha particle, hit the plasma, and it's going like that field to the fourth power. So you build an experiment where that field is as large as you can do it. And here again, this is, I could dispute with, these are the definition. Like in a fission reactor, you define the K effective that correspond to being critical. You define in a fusion reactor a Kn, which is the power of the heating nuclei, divide the power of the heating nuclei plus the external heating. When that is 1, that means ignition. ITER is not designed to get that equal to 1. And that is the infamous Princeton parameter. Princeton, we all come from Princeton, we have no regrets about it. But they invented that parameter, and, which is called Q. Is the,
We're going to get about 3 minutes.
I'm finished. I can, yes, even now. You take the power of the alpha particle plus the neutrons go out, divide the heating power, and you define that Q. That doesn't mean that the machine makes, if Q is equal to 1, the same power that what is being put in. Okay, and the TFTR was supposed to get Q equal to 1, but if it got Q equal to 1, it did not mean anything. And the same is to be said about the ignition facility, National Ignition Facility at Livermore. Even their definition of ignition was not correct. So I don't think I want to go further. These are technologies that are, there are all sorts of new technologies. These are the Russian system. And I just want to show this one.
Your typical 10 minutes talk. From plasma physicists, they're all like that. Including me.
No, I just want to say, last figure, there is a future because in the technology of high-field superconductor, there have been dramatic advances. And you can make hybrid magnet where you make superconductors, certain magnet where you have magnesium diboride on the inside, and superconductor at liquid nitrogen temperature. You go to 30 Tesla, 25. So there is a big future along this line of work.
I think we better
yes,
close.
comment. And
I have one comment.
Tom O'Neill.
Please.
My name is Tom O'Neill.
Oh, Tom.
I'm a plasma physicist, but I've really never worked on fusion. And I'm afraid that a misconception is coming across here, and I want to clarify.
Tom, come up where you can use a...
Get the microphone.
I actually actually started plasma physics in 1992, about the time you were working at Los Alamos. And
61.
I mean, that's what I meant, 1962. You were 1961. At that, there is a scientific criteria for how close you are to break even, and that is called the Lawson criteria. It's the product of the density times the confinement time. In 1961 and 1962, we were orders of magnitude away from the criteria for break even. Since that time, there has been exponential growth in the quality of the Lawson criteria to where it is now within maybe a factor of 2 or 3. Faster, that progress has been faster than Moore's Law, I believe. So it's not just that governments are throwing money at this program for no progress. There's been dramatic progress in the understanding and quality of the plasma physics confinement. Now, it's true that ITER has many problems, mainly managerial problems. It's an incredibly complex system, management system. But the plasma physics has made tremendous progress. Thanks.
Okay, thank you. Yes, Charlie?
I think I'd much like to continue this, but I think I will try to give a few valedictory remarks so that we can move on. And the first thing I want to say, I think one of the reasons I got ahead in life is that I agree with everything I hear, including, including what Lou said. So I'm going to give you what I think over the long-term issue for, my own view of the long-term issue for fusion. As you get older, you begin to worry about sustainability. You think of your own, first of all, and then of your families. And then ultimately, if you're really philosophical, you'll think about the sustainability of our society. And on schedule, at reaching a certain age, I started working in sustainability. So what is the role of fusion in sustainability? It's absolutely clear to me that you cannot imagine our civilization going 2 or 3 centuries more after we've exhausted the useful fossil fuels, after we've reached the technological limits of wind and solar and so forth. We're still going to need clean power. And so the argument for fusion is that it's essential for the long-term stability of an advanced technical civilization, one that lives astronomical periods of time. And this is the argument that has sustained it. And it's a philosophical argument, and it leads always to underfunding. Because the problem is one of time scale. There's a mismatch between the time scale in which human society, let me put it this way, I also think the principal instability in the present program is not scientific, but it is the interaction between science and management. Yeah. And the incentives are all wrong. Politicians and even people like us are not going to invest in a project that produces results 5 generations ahead. So the incentives are misaligned, very hard. It's the same problem with climate science, by the way. And so it's very difficult to sustain a major program for long periods of time.
Yeah, Charlie, may I interrupt if you don't mind? I think we made it long term. I mean,
yeah.
The only where I object is that there was no need to make it such long term. We should have proven the scientific feasibility of fusion by now. Scientific. To make a source is a different story, a useful source. But there is no, the scientific feasibility can be proven in a short time.
Yeah.
So the fusion is not so far away, 5 generations and so on. If you go with ITER, yes.
Yeah.
ITER is 5 generations.
Pardon me? Yeah. So I think you've got a sense of the basic issues associated with the fusion program. My own view is that it's one of the most challenging branches of physics.
The interface between physics and technology is one of the most challenging ever tried. It will take a long time to achieve, and the principal problem will be to sustain support for a rational program, which ITER may not be for a long period of time. It is one of the first intergenerational scientific projects ever conceived, and the management conceptions for managing intergenerational projects are very different. And we're going to encounter that shortly in space science when we go and start developing large global projects that will take decades to complete and to continue.